In this video, I'll go through two-way analysis of variance. So this is where we have more than one factor in our analysis in our data set. So for the first example, this is an example of a randomized block design. So we have air traffic controllers, and they are testing out three different workstation alternatives. So system A, system B, and system C. Now we have 6 air traffic controllers, and they each test each system, and then their stress is measured. So controller 1 had a stress of 15 when he or she used system A, 15 again for system B, and 18 for system C. And our primary interest is in seeing if there's any difference in the workstation systems. So the mean level of stress for system A, B, and C, are they the same or different? And by having the same controller experience each different system, the controller is acting as a block. And that's why this is called a randomized block design. And it allows us to get a more precise estimate of differences between the systems when we design this way. So our analysis of variance, there's formulas we can use to calculate this from scratch, but we don't really want to do that. That's a lot of work, and when we can just click a few buttons and get a computer to give us the output for nothing, it doesn't really give us much benefit. So we're going to jump straight to Excel stat and under modeling data, ANOVA. And then we'll pick our variables. So we're using the air traffic data set. So this is our response variable, our Y variable. And then now we have 2 qualitative variables, not that one. Let's try that again. 2 variables, system and controller. And let's just make sure everything's set up the way I want it to. I'm resetting everything to its default values actually, except under outputs, I'm going to select underneath where it says analysis of variance, it says type 1/2/3 SS. SS stands for sums of squares. And I'm going to check that. By default, it's unchecked, but I'm going to check it because that will allow us to separate the effect of the system from the controller. So we'll OK that. And take a look at the results when they're ready. Okay, so we'll scroll again, lots of output that we're not going to really take too much time with, or any time in fact. We're going to go straight to the analysis of variance table. So here's the analysis of variance table, and you can see that there's 3 rows, the total, and a row for the error, and then a row for the model. But what I want to do is I want to separate out the system effect and the controller effect. And that's what this extra bit of output down here is. Under type 1 sum of squares analysis, it has a separate row for system and controller. I'm not really interested in the controller. What I'm really interested in is if there's differences in the systems, because that's the focus of the study. So I have 2 degrees of freedom because there's 3 systems, and degrees of freedom is 3 minus 1 or 2. Sum of squares there is 21. Mean square is 21 divided by 2, so 10.5. Then the F statistic will be 10.5 divided by the error mean square, the mean square error, 1.9. That comes to 5.526. And then the p-value, 0.024, comes from an F distribution with 2 numerator degrees of freedom and 10 denominator degrees of freedom. So what I've done is I've copied this information and this information into the analysis of variance table here. Okay, so we were just looking at this p-value here, 0.024. Our decision criteria, as always, set a significance level and ask ourselves, is the p-value less than the significance level? If it is, reject the null hypothesis in favor of the alternative. So 0.024 is less than 0.05. So we reject the null in favor of the alternative and conclude that there are differences in the systems, that the mean stress for each system, it's not the same. So that's the conclusion there. Let's look at another study. This one is Gmat scores for applicants to different colleges, and they've studied using different methods. So one set of students has used just a 3-hour review session. Another set of students has used a 1-day program, and another set of students has used a whole 10-week course. And what we're interested in is whether there are differences amongst the programs. So in particularly, would the 10-week course be more effective than the 1-day and 3-hour courses? And then are there any differences between the colleges as well? So we have 3 colleges and 3 programs, and for each college, there were 2 students each that did each program. So in total, we've got 18 students here represented, and these were their Gmat scores. And so again, we're going to just use XLStat to do the analysis of variance for us rather than grinding out all those calculations to do it by hand. So we'll go to modeling data, ANOVA, and then we'll select our data. So Gmat study, the scores, and then the qualitative variables are program and college. And this time under options, where it says interactions, I'm going to check that because we're going to do what's called a full factorial analysis. So we have 2 factors in this example, the college and the program, and we're going to look at not just the effect of college by itself and the effect of program by itself, but also whether there's any interaction between those 2 in how people's scores, applicant scores vary. So by checking that box, that will allow us to pick the interaction to be included in the analysis. And then now if I click OK, it'll ask me which factors and interactions I want to include, and I want program, college, and program by college interaction. So I want all 3 of these. So I'll click OK. And then again, we'll just focus on the analysis of variance table. Once it's finally done its thing. Okay, here we go. So I'll scroll down to the analysis of variance table. Again, here's the summary, which has a row for the model, the error, and the total. But I want to break down this model row into component pieces. One will be for the program, one for the college, and one for the program by college interaction. So these 8 degrees of freedom here are split into 2 degrees of freedom for the program, because there's 3 different programs. 2 degrees of freedom for the college, because there's 3 colleges. And each time the degrees of freedom is the number of levels minus 1. And then the program by college interaction is 2 times 2. There's 4 degrees of freedom for that. And that adds up to the 8 for the model up here. And the sum of squares is this 62,600 is partitioned between those 3 different effects. Then the mean squares are calculated in the usual way, just sum of squares divided by degrees of freedom. And then there's an F statistic for each of the different effects. And the F statistic for program will be the mean square for program divided by the mean squared error. The F statistic for college will be the mean square for college divided by the mean squared error. And the F statistic for program by college interaction is the mean square for the interaction divided by the mean squared error. And there's p-values for each of those F statistic. And so what I've done again is I've copied this part of the overall analysis of variance table and this section here into the original sheet, just so we can focus on what's most important for us. Okay, so let's look at the results. So for program, this p-value, so this is the right tail area corresponding to an F statistic with 2 numerator degrees of freedom and 9 denominator degrees of freedom. And it comes to 0.299. It's not significant at the 0.05 significance level. So this tells us that there's no significant difference between the different programs, which is perhaps a little surprising. You would hope that that 10-week course would be a little more effective than the other ones, but the results here suggest that there aren't significant differences. On the other hand, there are significant differences amongst the colleges. So this F statistic here has a right tail area of only 0.005. And the F distribution that's being used here has 2 numerator degrees of freedom, 9 denominator degrees of freedom. So it's significant, so we reject the null hypothesis in this case and conclude that the means for the colleges are not all the same. And then finally, the interaction has a F statistic of 1.270. It's not significant. For an F distribution with 4 numerator degrees of freedom and 9 denominator degrees of freedom, we get a p-value of 0.350, and that's not less than 0.05. So we would conclude that there's no interaction effect going on here. So often, after a result like this, some analysts will go on to fit another model that excludes the interaction, given that it's not significant here. So actually, let's do that just to see what happens. What will happen is the whole model will be re-estimated without this row. There'll be additional degrees of freedom available to estimate the error. So the mean squared error will change, and then these numbers will change as well. And so will the p-values. So let's see what happens. So we'll call our analysis of variance again, and this time we'll unselect the interaction, or deselect it, I guess is a better word. And then we'll look at the results and see if college is still significant, but program is not. Okay, so here's what we want to look at. And yeah, that conclusions remain the same. We have a significant result for college, but not for program. So that's an example of analysis of variance with multiple factors. We looked at 2 factors in this case, so we did two-way analysis of variance. In the first example was for a randomized block design where one of the factors, controller, was used as a block, and so we weren't really interested in that in and of itself. It was just being used to give us a more accurate notion of differences amongst the systems. And then in the second example, we did a factorial analysis, and we had 2 factors of interest, and then we also looked at the interaction.